Welcome to The Explainer. Today, our goal is highly specific, but honestly, it's incredibly powerful. We're going to completely demystify machine learning. So often this term gets thrown around like it's some sort of digital magic, right? Or just this inscrutable black box. But by the time we wrap up today, we're going to transform that magical buzzword into a highly structured, totally logical process. We're basically going to break down exactly how a computer learns from data, and we're going to make the whole process completely accessible. Let's get into it.
Here's our roadmap for today. We'll hit the core ML problems, look at classification versus clustering, contrast classification with regression, cover some essential vocabulary, and finish up with the steps to build a model.
All right, Section 1, the core ML problems. What exactly are we solving?
I actually want to toss this fundamental question right over to you. What exactly is machine learning trying to solve? I mean, we all know it involves computers and massive amounts of data, but what's the actual end goal when we feed a machine all of this information? What's the point?
Well, it really comes down to this. Machine learning is essentially a programming technique that lets computers solve problems without us having to explicitly program them for every single possible scenario. Instead, the system looks at past experience, which, is just what we call data, to learn decision-making, predict outcomes, or hunt down hidden similarities and patterns. It's a huge shift. We're moving from rigid, hard-coded programming to truly adaptable learning.
And if we distill all of that down, almost every machine learning problem out there fits neatly into one of four specific buckets. First up, we've got regression. That's for predicting a continuous value, like, say, figuring out the expected cost of a piece of real estate. Next is classification, which predicts a discrete category. Think of an algorithm deciding whether a movie review is positive or negative. Then there's clustering. This one groups similar data points together, but without any predefined labels. And finally, we have ranking, which is just ordering groups of instances based on specific criteria. Grasping these four pillars, that is absolutely crucial. It's the bedrock for everything else we're going to discuss.
Moving right along to Section 2, classification versus clustering, drawing the lines.
People constantly get these two mixed up, so let's think about it using a really simple drawer analogy. Classification operates in the supervised learning domain. That means you already know what the drawers are labeled, say cats and dogs, and your goal is to put each new individual into the correct specific drawer based on certain grouping criteria. Clustering, on the flip side, is unsupervised. There are zero predefined labels. The algorithm simply senses the differences based on the math and the variables, and it dynamically builds those drawers based on similarities. It's only after the math groups them together that a human steps in and tries to assign some logical meaning to those clusters.
Now, what's really fascinating is how we can anchor those abstract definitions into actual visual geometry. If you map it out, clustering looks like data points grouped into circular boundaries, based purely on how close or similar they are to each other. But for classification, you'd actually see a clear, distinct boundary line separating, say, yellow dots from green dots. The algorithm has actively drawn a line in the sand to categorize new data into known, predefined outcomes.
So the real kicker here is the data requirements. Because classification has a very specific objective, finding that predefined class, it is fundamentally a more complex process. It absolutely relies on having a heavily labeled training and testing dataset to learn from. Clustering, it doesn't need that training data set at all, because its only objective is to find relationships and group objects together based purely on their inherent statistical similarities.
Okay, Section 3, classification versus regression. Let's look at these supervised methods.
To really nail down the difference between these two predictive powerhouses, I want you to think about an incredibly relatable question. What is tomorrow's weather going to be like? Believe it or not, exactly how you choose to answer that question completely determines which algorithm you need to use. Check this out. If you want to know the exact temperature tomorrow, like predicting it's going to be exactly 84 degrees, you're dealing with continuous output. That makes it a regression problem. But if you simply want to categorize tomorrow as either hot or cold, which is a discrete output, now you're dealing with a classification problem. It's the exact same subject, just approached with two entirely different predictive goals. Pretty cool, right?
Let's bring all that together and compare them head to head. Regression algorithms use continuous data to map inputs to a continuous output variable. And visually, they're trying to find a best fit line right through the middle of the data. Classification algorithms, however, use discrete data to map inputs to a discrete output, and they are trying to find a decision boundary that divides the data set into distinct classes. So it's a line versus a boundary, continuous versus discrete.
Moving on to Section 4, essential vocabulary. Time to learn the lingo.
First up, we have Epoch.
An epoch simply describes the number of times the machine learning algorithm sees the entire dataset during its training phase. You can kind of think of it like the number of complete passes the machine makes through its study material to really learn those underlying patterns.
Next up is a major pitfall: overfitting. This happens when your model basically memorizes the test instead of actually learning the underlying concepts. It learns the training data a little too well, absorbing all this random, irrelevant noise. And the real danger here? While the model might look absolutely amazing in training, it's going to perform terribly the second you introduce it to unseen real-world data.
And then we've got the confusion matrix. Now, despite the name, its entire job is actually to make sure you aren't confused. It basically acts as the ultimate report card for a classification model's guesses. It breaks down performance into true positives, true negatives, false positives, and false negatives. In plain English, it tells you exactly where and how your model is getting confused.
All right, final section, Section 5, Steps to Build a Model, the ML Recipe.
Theory time is over. We're the chefs now, and it's time to cook up a real machine learning model using a proven 7-step recipe. Step 1 is data collection, and honestly, I cannot stress this enough. The quantity and quality of data you collect here entirely dictates the accuracy of literally everything that follows. It's the classic garbage in, garbage out rule. Step 2 is data preparation. This is where you clean up errors, handle missing values, and randomize the data to strip out any biases. Step 3 is choosing the right model based on those problem types we discussed earlier. Is it regression, classification, clustering? And step 4 is training the model, where the algorithm iteratively learns all those juicy patterns from your freshly prepared data.
Once it's trained up, we move right into step 5, evaluating the model. This is where we test it against a subset of data it has completely never seen before, just to measure its objective performance. Step 6 is hyperparameter tuning. And this is fascinating because our sources explicitly describe this step not just as a strict hard science, but really as an art form. This is where you tweak high-level properties like the learning rate or the overall complexity of the model just to squeeze out that little bit of extra performance. And finally, step 7 is making predictions. This is the big moment. You deploy the model against your final, withheld test set data to see how it's truly going to perform out there in the real world.
So we've traveled all the way from abstract definitions down to a concrete 7-step process. As you've seen, machine learning really isn't magic. It is just a highly structured, super-logical approach to solving complex problems using past experience. So, now that you know the recipe, you've got the tools, and you understand the language, what machine learning problem are you going to solve first? Thanks for hanging out with me for this explainer, and definitely keep learning.